Today we will start a new chapter, Torsion of Circular Shafts. So it is the second chapter in module 4. So we have covered bending stress and shear stress in module 4. The second chapter is this torsion of circular shafts. So we have discussed in center of materials till now the direct stresses, which is normal stress. Normal stress means tensile and compressive stresses. Then we discussed about shear stresses. They all represent the strength of a particular section of a material. Depending on the type of the material, you have different values of stresses that are going to be induced in the member. Then we discussed about the compound stresses and bending moment diagram, shear force diagram. Then bending stress and shear stress, bending compressive, bending tensile, and as well as shear stress distribution, how it varies across the cross section. So those things we have discussed. Now the next one is the torsion. So you might have seen this. So torsion means, given a sketch here, see here, this is a rod which is fixed at one end and it is free at the other end, like a cantilever. Now when this rod is subjected, this rod is called as shaft. So it is circular in shape. So whatever we are doing in this chapter, in torsion chapter, we consider only circular or hollow circular, only two types. We are not having any rectangular or square shape cross section. We are going to discuss only circular and hollow circular sections. So non-circular sections are not covered. So it is fixed here. Suppose if this shaft or the rod, whatever it is subjected to a twist like this. Twist means in one end it will be like this, in another end it will be like, see, so you have got one end it will be clockwise, another end it will be anti-clockwise. So of course here it is there's a mistake here. This arrow should come here. So one end it is clockwise, another end it is anti-clockwise. So it is anti-clockwise only. I think if you take this side, so this is clockwise. If you see across the cross section, one end will be subjected to clockwise, another end will be anti-clockwise, like this. So when a twisting moment acts in opposite directions, see here, when equal and opposite torque, so that is called as torque, are applied at the ends of a shaft, torsional moment develop. The effect of the torque is to twist the shaft. So what is the effect of the torsional moment? So you have studied about bending moment. So the main difference between bending moment and torsional moment is, in bending moment, the rod or the shaft will bend like this. Will bend like this. So bending moment will be like this. So whereas in torsional moment, you will be having torsion at both the ends. At one end, it will be in one direction. In another end, it will be in another direction. So that is known as your torsion. Actually, there is a mistake here. You can please make that correction. Here it is clockwise. Here it should be anti-clockwise, like this. Okay. So then in that case, what happens to the effect of this effect of the torsional moment on the shaft is it twists. Twist means this is how it is shown. If this is the axis of the shaft or the circular section, that axis will get shifted with some angle. So this angle is phi. Please note that this angle is phi. So whatever this angle between what is this B dash AB is phi. Since here I have taken A as fixed, there will not be any twist here, but there will be twist here at the free end. Just like your cantilever beam, bending moment will be there here. Therefore, you will not have any deflection here. Here also, since it is fixed, this end will not have any this phi value, but this end you will be having twist. Suppose if this is also not fixed, then definitely you will be having a torsion here also. So, but in all the cases, what we take is one end is fixed, the other end is subjected to torsion. This torsion experiment, of course, you are going to conduct in the lab also, BMT lab also. So here, this is the cross section. If you cut this, you are going to get a circular cross section like this. Y is the center of that circular cross section. R is the radius. Capital R is the radius of that shaft. Then this B and B dash look like this. And whatever angle made by this arc, BB dash arc, it is taken as theta. So please note that this is phi, this angle is phi, this angle is theta. So in the cross section, the angle is theta. In the along the length, it is phi. So I hope you understood. So here the moment is acting along the axis. If the load is applied perpendicular to the axis, then you will have bending moment. But here, what happens? Here the moment is applied along the axis, not perpendicular to the axis. Then it is torsion. So torsion means twisting. So the effect of the torsional moment is nothing but twist. So normally its unit is same as bending moment unit. It is kilonewton meter or Newton millimeter. So it is expressed as Newton millimeter or kilonewton meter, and this phi is called as the shear strain. Whatever angle here in radians, whatever angle, it is not in degrees, you have to take that angle in radians. Whatever phi you are going to get here, that is called as the shear strain. Shear strain, and since this phi will be very small, so phi will be very small, so phi can be equated to sine phi, and that can be equated to tan phi. So that you property you know from the trigonometry. When phi is very small and it is in radians, phi can be equated to sine phi and that can be equated to tan phi. So here, if you take sine phi, what is the or tan phi? What is the value of tan phi here? So tan phi will be bb dash divided by ab. So phi is equal to tan phi, bb dash divided by ab. So let me take that ab as the length of the shaft. Length of the shaft is taken as L. L is the length of the shaft. So that means it is bb dash by L. Then R is the radius of the shaft. See here. Then theta is the angle of twist. So in cross section, whatever angle is there, that is called as angle of twist. So angle of twist is different from shear strain. This is phi in longitudinal section. This is theta in cross section. So angle of twist is angle BOP dash. That is also in radians. So all the angles are taken in radians. Even if they give in degrees in the problem, that you have to take in radians. You have to convert the degrees to radians. So you know that 1 degree is pi by 180 radians. So all these things you should note down. Then what is the value of the BB dash? So BB dash is nothing but the arc of a circle. R is the radius, theta is the angle. Therefore BB dash will be R into theta. So that is a property formula in trigonometry. Length of the arc of a circle, subtend angle is theta, and radius is R, means it is R into theta. Thing is theta is in radians. Okay, BB dash is equal to R into theta. So therefore, what you can write here is, so this phi is equal to BB dash by AB. So BB dash is R into theta, AB is L. So therefore, we can say phi is equal to R theta by L. Please note that this theta is in radians. Theta is in radians. So this is the relationship between angle of this theta and the shear strain. So if you know R and L, you can find this. So phi is equal to R theta by L. Very simple relationship. Now, the experiments have proved that, so this is the cross section of the shaft, circular shaft. R is the overall radius, that is total radius. If you take any other layer, just like you are considering the layer in bending stress and shear stress, like that in torsion, if you take any radial distance, R1, R2 like that, so the effect of this torsion is that it will induce a shear stress. So very, very important. So you don't have any bending stress here, only shear stress will be induced. So shear stress will be there across the circle, that is at different radial distances. So experiments have proved that shear stress developed at any layer. Layer means these are the layers. See here, the circumference is called as the layer. So you have got so many different radial distances. You can have so many layers. So shear stress developed at any layer is directly proportional to distance of the layer from the center of the shaft. So this is the center of the shaft. This is the distance of the layer. R is the distance of the layer. Center of the shaft is O. Tau is the shear stress. So according to the statement, as R increases, tau also will increase. Since R is maximum at the outer radius, that is when small r is equal to capital R, you have tau is equal to tau max. So our tau max is also represented as tau s. Tau s. Tau s means maximum shear stress. So tau s is nothing but maximum shear stress. Where that maximum shear stress occurs? Maximum shear stress occurs at the circumference of the shaft. So if you take different radius here, different radius, you will be having different values of shear stress. So from the center, as you move in the radial distance, when you move, when the value of radius increases, your tau value also will increase. So shear stress ಜಾಸ್ತಿ ಆಗ್ತಾ ಹೋಗ್ತದೆ. So radius ಜಾಸ್ತಿ ಆದಾಗೆ shear stress ಜಾಸ್ತಿ ಆಗುತ್ತೆ. So mathematically it can be written like this: tau is directly proportional to r. ಗೊತ್ತಾಯ್ತಾ? ಸೊ ಅಂದ್ರೆ tau is equal to, ಈಗ ಏನಾಗುತ್ತೆ, ಇಲ್ಲಿ actually ಇದು small r ಇದೆ. Tau is directly proportional to small r. Tau is the shear stress, r is the radius, directly proportional. ಅಂದಾಗ if you remove that proportionality sign, you can introduce is equal to ಹಾಕಿದ್ರೆ ಒಂದು ಕಾನ್ಸ್ಟೆಂಟ್ ಬರುತ್ತೆ k. So tau is equal to k into r ಅಂತ ಬರುತ್ತೆ. So if you want tau 1 is equal to k into r1. If you want tau 2 is equal to k into r2. So k is constant. K is a constant. So but ಯಾವಾಗ maximum ಆಗ್ತದೆ, when small r is equal to capital R, then tau becomes tau max. That's what. So ಅವಾಗ ಏನಾಗುತ್ತೆ, tau max, maximum shear stress occurs at the circumference of the shaft or boundary of the shaft. You can write it as boundary also. Circumference means boundary. So ಅವಾಗ ಅದಕ್ಕೆ ಎಕ್ಸ್ಪ್ರೆಷನ್ ಏನು, tau s is equal to k into r, capital R, at the circumference. When r is equal to 0, ಹಾಕಿದಾಗ ಇಲ್ಲಿ tau is equal to 0 ಆಗ್ಬಿಡುತ್ತೆ. ಅಂದ್ರೆ if you at the center of the shaft, O, r is equal to 0. So when r is equal to 0, you will be getting tau is equal to 0. So tau is equal to 0 at the center. Tau max is also written as tau s, that is equal to k into r. So this is the, at the circumference, this is the shear stress value. At the center, this is the shear stress. So these two you should keep it in mind. So maximum shear stress occurs at the boundary of the shaft. Tau is maximum at the boundary of the shaft. That is at r is equal to capital R, and it is 0 at r is equal to 0. There is no shear stress at the center according to this equation. So shear stress is directly proportional to the distance from the center, radial distance from the center. So ಅದರ ಪ್ರಕಾರ ಏನಂತ ಬರೀಬಹುದು ನಾವು, so tau 1 is equal to k into r1, tau 2 is equal to k into r2. ಅದನ್ನೆಲ್ಲ ಬರೆದಾಗ everything, if you take k outside, so k will be equal to tau 1 by r1, tau 2 by r2, tau 3 by r3, like that you can write, and finally it is tau s by rs, where tau x is the maximum shear stress. So tau s means maximum shear stress that is occurring at the boundary of the shaft. Shear force, ಈಗ shear stress tau ಆದ್ರೆ shear force ಏನಾಗುತ್ತೆ, shear stress multiplied by the area. Suppose if you take an elemental area here, dA is an elemental area here. If you take, if tau is the shear stress there, what is the shear force acting there? Shear force will be F is equal to tau into dA. Shear stress is shear force divided by area, or shear force is shear stress multiplied by area. So tau into dA is your F. Next, what is the torque? What is the relationship? So tau, once you know the value of tau, F can be found out using tau into dA. Then torque T is given by whatever shear force is developing there multiplied by the radial distance. That means F into R. So F into R is the torque. Torque is denoted by T here. So torque, twisting moment, there are a torsional moment. So ಮೂರು ಒಂದೇನೆ. So all the three are same. Three wordings: torque, torsional moment, twisting moment. So when a rod or a shaft, that rod anta kariyalla illi shaft anta kariyತೀವಿ, torsion ಅಂದ್ರೆ shaft ಅಂತಾನೆ ಕರೀತೀವಿ. So when the shaft is subjected to torsion means it is the moment at equal and opposite moment acting at the two ends of the shaft. ಅದನ್ನ ನಾವು shaft ಅಂತ ತಗೊಳ್ಳೋದು, ಆಯ್ತಾ? So now we will see how the derivation can be done for the pure torsion equation. So here let us see how derivation can be done. One is just like pure bending equation, you have got pure torsion equation also. So illu ಅಷ್ಟೇ, ಯಾರೋ ಏನಾಗಿದೆ ಮಿಸ್ಟೇಕ್ ಆಗಿದೆ, ಯಾರೋ ಒಂದು ಕ್ಲಾಕ್ ವೈಸ್ ಇದ್ರೆ ಇನ್ನೊಂದು ಆಂಟಿ ಕ್ಲಾಕ್ ವೈಸ್. ಒಂದು ಅಂದ್ರೆ ಈ ಕಡೆ at this end if it is twisted like this, at the other end it will be twisted in the other way. ಇಲ್ಲಿ ಈ ತರ ಟ್ವಿಸ್ಟ್ ಆದ್ರೆ ಇಲ್ಲಿ ಇನ್ನೊಂದು ಆಪೋಸಿಟ್ ಡೈರೆಕ್ಷನ್ ಅಲ್ಲಿ ಆಕ್ಟ್ ಆಗುತ್ತೆ ಹಾಗೆ. ಓಕೆ, ಸೊ ದಟ್ ಇಸ್ ದಿ ಮೀನಿಂಗ್. ಅಫ್ ಕೋರ್ಸ್ ಐ ಥಿಂಕ್ ನಾನು ಬರ್ದಿರೋದು ಕರೆಕ್ಟ್ ಅಂತ ಕಾಣುತ್ತೆ ನೋಡಿ. ಈ ಕಡೆ ಇಲ್ಲಿ ಟ್ವಿಸ್ಟ್ ಈ ತರ ಆದ್ರೆ ಇಲ್ಲಿ ಹೀಗೆ ಹೋಗ್ತದೆ, ಅವಾಗ ಏನಾಗ್ತದೆ, ಎಂಟೈರ್ ಮೆಂಬರ್ ವಿಲ್ ಗೆಟ್ ಟ್ವಿಸ್ಟೆಡ್ ಲೈಕ್ ದಟ್. ಓಕೆ, ಸೊ ಅಸಂಪ್ಷನ್ಸ್ ಇದೆ. ಸೊ ಸೇಮ್ ಫಿಗರ್, ಅಲ್ಲಿ ಏನ್ ಫಿಗರ್ ಬರ್ದಿದ್ದೀನಿ ಅದೇ ಫಿಗರ್ ಇದೆ ಇಲ್ಲಿ. ಇದು ಲಾಂಗಿಟ್ಯೂಡಿನಲ್ ಸೆಕ್ಷನ್, ಕ್ರಾಸ್ ಸೆಕ್ಷನ್, phi is the shear strain, theta is the angle of twist, okay, T is the torque or the torsional moment or twisting moment. L is the length of the shaft. R is the radius of the shaft. These two notations. So some assumptions are made in deriving this equation. Simple derivation, two steps. You have two stages. You are going to derive this equation. Just like your pure bending equation, you have got this pure torsion equation. So pure torsion equation, when a shaft is subjected to only torque, this equation is used. So material of the shaft is homogeneous and isotropic. Same assumption we are using there also in bending equation also. Material. So the homogeneous means it has got same physical properties in all the directions. Isotropic means it has same elastic properties in all the directions. Young's modulus is same. Poisson's ratio is same in all the three directions, means x, y, z direction, along the length, along the diameter. That is the meaning. Twist along the shaft is uniform. So we assume that this angle of twist is uniform throughout the shaft. The cross section of the shaft remains plane before and after the twist. So that circular cross section remains as it is. There will not be any difference in the cross sectional area even after the twist. That is the meaning. All radii which are straight before twist remain straight after twist. So whatever radius are there in this, so the radius remains straight only. It will not have any deviation, buckling like that. Okay. So these are the four important assumptions. Now very simple derivation. You can see here. I have told you that this phi is equal to tan phi because phi is very small. B dash divided by AB. So from that, so B dash is nothing but r into theta from this diagram that I have explained. Arc of the circle is equal to radius into this theta when theta is in radians. So if you substitute that, you have got that phi is equal to r theta by L. Now, according to the definition of modulus of rigidity, here we are not taking Young's modulus. Here we take shear modulus or rigidity modulus or modulus of rigidity, which is denoted by G or C. Some books they use C, capital C. Some books they use G. Anyway, in some problems I might have used the C here. Whether it is C or G, they are same. Please note that. In the question paper, they may give modulus of rigidity as either G or C. So G is equal to, what is the definition of shear modulus? Within elastic limits, it's the ratio of shear stress to shear strain. So shear stress here is tau s. So we will consider maximum shear stress. So tau s is the maximum shear stress at the boundary of the shaft divided by shear strain is phi. So G is nothing but tau s divided by phi. So therefore, tau s is equal to G into phi. G into phi. So therefore, now substitute for phi as r theta by L. Phi is nothing but r theta by L. Substitute this here. Now, if you simplify this, what is that you are going to get? Tau s divided by r is equal to g theta by L. So this is one expression. So starting from the definition of phi and g, we have arrived at this. This is, we call this as equation 1. Tau s is the maximum shear stress at the boundary of the shaft. R is the radius of the shaft. G is the shear modulus. Theta is the angle of twist. L is the length of the shaft. Next, second part. Now let us take tau as the shear stress at the distance r, small r. So what I will take is at any radial distance r. Now I am not taking capital R. I am taking at any radial distance small r. If I take dA as the small area, F is the shear force acting over that area. Then F is given in shear force. F is given by tau into dA. That's how I have explained. So tau into dA, shear stress into area gives the shear force. If you want the torque I will call it as dt. Because I am taking small area, torque I am going to take is the torque is acting over that smaller area. That is dt. So dt will be F into R. So F into R is dt. F is tau into dA into R. So this is the expression for the torque. Now, according to the principle, that is law, so we have seen that the shear stress is directly proportional to the radial distance. So this we can write. Tau divided by R should be equal to tau s by capital R. So this I have explained here. Because shear stress is directly proportional to, see this is one. Shear stress is directly proportional to the distance, radial distance from the center of the shaft. So you can write like this. So you can write it as tau by R is equal to tau s by R, because Tau is the shear stress here, R is the radial distance. Then tau S is the shear stress of the circumference, capital R is the radius. So tau by R is equal to tau S by R. So where tau S is nothing but tau max. Now from this, what is tau? Tau is R into tau S divided by R. Now we have got this. Now in this dt expression, torque expression, tau into dA into R, substitute for this tau. So tau can be written as tau S into R divided by R into dA. So if you integrate this, what you will get? So you will get T here. So dt is the torque over the smaller area. Capital T is the torque over the entire area. Total area. Okay, that is A. If A is the total area, capital T is the torque acting over the total area, which is nothing but the integral of this. So which is nothing but torque acting on the entire shaft. So if you integrate this, what you will get? Integral dt is equal to tau S divided by capital R into integral R square dA. Because here tau S and R, they are constants. Maximum shear stress and radius, they are constants. You can take it outside. So integral R square dA. So according to the definition of polar moment of inertia, so polar moment of inertia you have studied in your mechanics, engineering mechanics. According to the definition of the polar moment of inertia, which is denoted by IP, or some books they use capital J. Please make a note of that. So IP or capital J, it is known as polar moment of inertia. That is defined as integral R square dA. So that you should remember. So integral R square dA is your IP or J. So what is actually polar moment of inertia? Polar moment of inertia is defined like this. Ix plus Iy. If you have, suppose if you have a circular section like this is circular section, x-axis is this, y-axis is this, R will be this. So if you take the coordinates of any point here, so that radial distance, you will have a Pythagoras theorem you can apply for the right angle triangle. This will be x, this will be y, this will be r. So r square is equal to x square plus y square. So integral r square dA is polar moment of inertia. Integral x square dA. Integral x square dA is Iy. Integral y square dA is Ix. According to the definition. This is y square dA. This is x square dA. So if you add them, so you are going to get the polar moment of inertia. So if you add these two, you will get, if you add these two integrals, integral x square plus y square dA, which is x square plus y square is nothing but r square. So therefore IP is equal to integral r square dA. So this is how the polar moment of inertia is defined. So what you do here is, if you are getting here you are getting integral r square dA term, this is nothing but your IP. So that means polar moment of inertia IP or capital J. So this integral dt is T, tau S by R is constant into IP. So this is IP. So this you can write it as T by IP is equal to tau S by R. So this is the another equation. So two expressions we have got, two expressions we have derived. This is one expression. Here we got tau S by R is equal to G theta by L. Here we got tau S by R is equal to T by IP. LHS are same in both the equations. You compare, you can write together, both the equations you can write together like this. Tau S by R is equal to G theta by L is equal to T by IP. So this equation is called as the pure torsion equation. So this is similar to your bending equation. In bending equation, what you get? M by I. So here, instead of M, T is there. Instead of I, IP is there. Okay. Is equal to F by Y. F by Y. F by Y means here, instead of F, you have got G theta. Instead of Y, you have got L. Okay. Is equal to E by R. Instead of E, you have got tau S. R remains as it is here. See. So that is the comparison between bending equation. M by I is equal to F by Y is equal to E by R. This is torsion equation. T by IP is equal to G theta by L is equal to tau S by R. Okay. So there are two steps in the derivation of torsion equation. In the first step, we have got from the definition of phi and G, we got this relation. In the second step, we have written the expression for the torque acting over a smaller area dt, which is given by tau into dA into R. Here tau into dA is the shear force multiplied by the radial distance gives the torque. Shear force multiplied by radial distance gives the torque. When that torque is integrated over the entire area, you are going to get this equation where IP is integral r square dA. So integral r square dA is IP. So if you compare 1 and 2, finally you are going to get this equation. So if a member is subjected to only twisting moment, the member is said to be in pure torsion. So this equation holds good only if torsion moment is acting on a shaft. When bending moment is acting, this equation does not hold good. Similarly, pure moment equation, pure bending equation is applied only when there is bending moment, when there is no torsion. So these are separate. So torsion equation you have to use only when torsion is acting on the shaft. Pure bending equation you have to use only when bending effect is there on the element. That is the meaning. Okay. Now let us see the units of all this, because for doing problems, you should be very careful. Let us see what are the units of this. There are some 7 quantities here. 1, 2, 3, 4, 5, 6, 7. Here, let us see in all the problems. We will restrict to one unit. So let us take this torque in Newton millimeter. Okay, not in Newton meter. You can take in Newton millimeter. Torque will be in Newton millimeter. IP, polar moment of inertia, in millimeter power 4. Just like your I value, moment of inertia value. G is modulus of rigidity or rigidity modulus or shear modulus. G, sometimes in some books they use C. Please make a note of that, capital C. That is expressed in Newton per mm square or MPa. Theta is the angle of twist is in radians. L is the length of the shaft in millimeters. Tau s is the shear stress in Newton per mm square or MPa. R is the radius of the shaft in millimeters. So let us stick on to Newton and millimeter and radian. So that is the unit. For doing problems, if they give in any other unit, before substituting in the formula, we have to convert to this unit and we have to substitute and simplify. Please remember that. Now let us see how the value of that polar moment of inertia is obtained for circular and hollow circular sections. All this we have learned in your engineering mechanics in moment of inertia chapter. Anyway, I will repeat. So here, for a solid circular shaft means there is no hole. So it is not hollow. There is no hole. It's a solid circular shaft. So what is the value of moment of inertia? It is pi d power 4 by 64. About both, so x-axis and y-axis, about both the axes, it is pi d power 4 by 64 because of symmetry. So you know that polar moment of inertia, IP, or capital J. In some books they use capital J. It is the sum of Ix and Iy. Actually, this is known as perpendicular axis theorem. In your moment of inertia chapter, engineering mechanics, there are 2 theorems. One theorem I told on that day, parallel axis theorem. This is called perpendicular axis theorem. So polar moment of inertia is equal to Ix plus Iy. So Ix and Iy both are equal to pi d power 4 by 64. This you should remember. Okay. So when you add these two, you will get pi d power 4 by 32. Or if you put diameter is equal to 2 times r, it will be simplified to pi r power 4 by 2. So if they give diameter, you can convert to radius and you can use this. If you put r is equal to d is equal to 2r, so 2 to the power 4 means it is 16. So 16 divided by 32 is half. So 2 will be there in the denominator. So pi d power 4 by 32 or pi r power 4 by 2. So these are the formula for, this is the formula for polar moment of inertia, IP, for a solid circular shaft. Suppose if it is a hollow circular shaft, see this is hollow. So here capital D is the outer diameter, small d is the inner diameter, and capital R is the outer radius, small r is the inner radius. This portion is hollow. So thickness is T here. So how to get thickness? T is equal to, you will be getting capital R minus small r. Okay, that is T. Now in this case also, what happens here? Ix plus Iy. Here also Ix is equal to Iy. So Ix for this case is, so the d power 4 is replaced by, d power 4 is replaced by d power 4 minus small d power 4. That is the answer. So here for a solid circular shaft, pi d power 4 by 32. For a hollow circular shaft, pi into d power 4 minus small d power 4 divided by 32, or pi into capital R power 4 minus small r power 4 divided by 2. So that is the formula for polar moment of inertia. See, so when they give solid circular shaft problem, we have to use that formula. Hollow circular shaft problem, we have to use this formula. So you have to remember this. So for polar moment of inertia. Now let us see what is the expression for maximum torque or the maximum torsional moment, Tmax. Where it occurs? It occurs at the boundary. So we know that maximum torque occurs at the boundary because maximum shear stress occurs at the boundary. At R is equal to capital R, maximum torque will be there. So tau is maximum at R is equal to capital R. Therefore, F is maximum at R is equal to capital R. Since shear stress is maximum there, shear force is also maximum there, and torque also is maximum there. So torque is nothing but shear force multiplied by the radial distance. Here radial distance is capital R. So therefore, in the pure torsion equation, what you can do is, so this is the pure torsion equation. Tau S by R is equal to T by IP. T by IP. Therefore, T is equal to Tmax if tau is equal to tau S. So that means tau S by R is equal to T by IP means tau S will be what you can write Tmax will be equal to, so this Tmax will be equal to, what is this thing? Tau S into IP divided by R. So that is the expression for the maximum torque which occurs at the boundary. At the boundary means at the outer circumference here. So here you have the maximum torque. At the center it will be 0. Okay. In the case of solid circular shaft also, you have the maximum torque here at the outer boundary, and at the center it is 0. You can just compare this with the bending stress. So bending stress, what happens? Bending stress is 0 at the neutral axis, but it is maximum at the farthest fiber. Okay, that also we have discussed. Similar to that, shear stress is maximum at the farthest fiber, means here it is circumference because we are considering circular and hollow circular sections. And when the shear stress is multiplied by the area, you are getting the shear force. When shear force is multiplied by the radial distance, you are getting the torque. So torque is maximum at the boundary of the shaft. So what happens for the solid circular section? For the solid circular section, Tmax is given by now tau S by R into, so whatever tau S by R is common here, IP is nothing but this pi d power 4 by 32, or you can take it as pi R square by 2, whatever you want. So IP value just only you have to put. For hollow circular section, if you put IP value, you will get the maximum torque. So this is about maximum torque. So actually here in this equation, pure torsion equation, whatever we have derived here, if you want, this equation can be used anywhere along the radial distance. Suppose this tau S by R, we know that this tau S by R is equal to tau by R also. See here, we have written here, we have used this here. Tau by R is equal to tau S by R. That means this tau S by R also can be written as tau by R. So if you use that equation, then what happens here? This becomes tau by small r. Tau by small r is equal to g theta by L is equal to T by I. So when you want maximum torque, we have to use this. Okay. Otherwise, the general equation is tau by small r, because tau by small r is equal to tau S by capital R. So this is what the torsion equation is, and the polar moment of inertia, and about maximum torque. Now there is another one, power transmitted by the shaft. So what happens when a shaft is subjected to torsional moment, power gets transmitted from one end to the other end. So this is how the mechanism will be. How do you define power? So power is work done divided by time. That you know from the definition of physics. Work done divided by time. Rate of doing work is called as power. So in this case, power is given by omega into T. So omega into T is power, where omega is called as the angular velocity. So angular velocity is given by 2 pi n by 60, where n is expressed in RPM. RPM means revolutions per minute. then 1800 like that they will give. Speed of the shaft, when the shaft rotates, normally its speed is represented in RPM, in revolutions per minute. That you have studied in your elements of mechanical engineering. So their rotation is always expressed in RPM, revolutions per minute, 80, 100, 500, 1000, 2000 like that. So when you know that, so n value, you can find out angular velocity using this formula 2n by 2 pi n by 60. So 2 pi n by 60 is known as the angular velocity. Actually, this angular velocity is expressed in radians per second. Please make a note of that. Angular radian per second. Radian per second is the unit of angular velocity. Then, if you substitute here, power transmitted will be omega into T. Omega is 2 pi n by 60 into T. It will be in watts. So, watt is the SI unit of power. So, power. So, these are the simple formulae which we are using in simple problems on torsion. So, torsion is a very easiest chapter. So, only simple derivations are there. So, today we discussed about the derivation of pure torsion equation, what is torsion, and how to arrive at the assumptions made in the derivation of torsion equation. And we derived the torsion equation. Then for solid circular section and hollow circular section, we got the expressions for polar moment of inertia. Then how to get the maximum torque. Maximum torque always occurs at the boundary of the shaft. That at small r is equal to capital R, you have the maximum shear stress, maximum shear force, maximum torque. So you should know the relationship between those three. So shear stress multiplied by the area gives the shear force. Shear force multiplied by the radial distance r gives the torque. So you know that maximum torque occurs at the boundary of the shaft. Then we discussed about the power. What is the expression for the power that can be transmitted by the shaft, which is nothing but 2 pi n t by 60, where sometimes omega may be given, angular velocity may be given. Angular velocity will be in radian per second. This n will be in RPM. Both are speed only, but it is expressed in different units. And this is the conversion, 2 pi n by 60. Now let us see one or two problems, simple problems on torsion. The shear stress in a solid shaft is not to exceed 40 MPa. So toe value is given here. Shear stress means toe. Toe is equal to, or toe, yes, you can write, because not to exceed means it is maximum value. So maximum value means toe s or toe max, which occurs at the boundary or the circumference. So toe s is 40 MPa, that is 40 Newton per mm square. When the torque transmitted is 20 kilonewton meter. So torque is 20 kilonewton meter. We are expressing Newton millimeter. 1 kilonewton meter is 10 power 6 Newton millimeter. Please note that. Because 1 kilonewton is 10 power 3 Newton. 1 meter is 10 power 3 millimeter. So if you multiply that, 10 power 3 into 10 power 3, you are going to get 10 power 6. So this is the conversion. So I told you to express in Newton and millimeter only. So these two are given. Find the minimum diameter of the shaft. So what is the diameter of the shaft? That is R value. Radius value you have to find out. From that, we can get the diameter. So very simple. So it is a very simple question. Tau s by R is equal to T by IP. Torsion equation we will use. So there are three terms in the torsion equation. Tau s by R is equal to T by IP is equal to G theta by L. So here we can use only this. So here IP is the polar moment of inertia. So polar moment of inertia of this solid circular section will be given by the formula pi d power 4 by 64 or pi r power 4 by 2. So here, of course, here it is expressed in terms of radius. So what is tau s here? Tau s is equal to T into R divided by IP. IP is pi r power 4 by 2. Now if you simplify this, you will get 2T divided by pi r cube. Now substitute the values. Substitute the values here, you will get R cube. So R cube is 2T divided by tau s into pi. So tau s is 40 into pi. T is 20 into 10 power 6. If you substitute that here and simplify, you will get R as 68.27. Diameter will be 2 times R. which is 136.554 mm. So that is the diameter of the shaft, diameter of the circular shaft that should be provided to maintain so that the shear stress won't exceed 40 MPa and the power torque transmitted is 20 kilonewton meter. Simple problem. Now, second problem, a hollow shaft. This is a hollow shaft of diameter. If I write like this, you don't confuse, this is diameter. A hollow shaft of diameter 120 mm transmits 300 kilowatt at 200 rpm. Determine the maximum internal diameter. This is external diameter. So it is understood. So you can write it as external diameter 120. So we have to find the maximum internal diameter if the maximum stress in the shaft is not to exceed 60 Newton per mm square. So here he has given power 300 kilowatt. So 300 instead of giving torque, he has given power itself. So see, this is the data given. Capital D, outer diameter, external diameter is 120 mm. P is that is what is that? No, N is 200 rpm. N is 200 rpm. Then this P is not there. Please this you remove it. P is not there here. It's a mistake here. You remove this P. P is not given. Capital D is the external diameter 120 mm. Then power transmitted P is correct. P is given. Yeah. For P is 300 kilowatt. Correct. P is 300 kilowatt. N is 200 rpm. Then maximum internal diameter is small d. Small d we have to find out. Okay. Capital D he has given. Small d we have to find out. And maximum shear stress is 60. Tau s is given. Okay. Now we have to use the formula for this power. So since power is given, P is equal to 2.2 by 60. This formula you have to use. From this formula, you get the value of T first. So what happens to the T value here? So T is equal to, if you want T, 60 into P divided by 2 pi. So 60 into P, 300 P is expressed, P has to be expressed in watts. 300 kilowatt means it is 300 into 10 cube watts. So 60 into 300 into 10 cube divided by 2 pi n. 2 pi into n is 200 rpm. So this is the formula. N should be in rpm. So if you simplify this, you will get this value. But this will be in Newton meter. Newton meter. Why it is in Newton meter? Because here kilowatt is there, you know. So this watt normally it contains meter. Meter as the SI unit for length. So you should be very careful here. So when you substitute in this, when you convert this watt, if you substitute in watt, you are going to get in Newton meter here. Later on, you have to convert that into Newton millimeter. So Newton millimeter. So what happens here? Next, after this, here you have to use the next equation, but that is torsion equation. Torsion equation is tau s by r is equal to T by IP. So if you use that equation, then what is the unknown there? So unknown is your capital small d. Unknown is small d. So here IP for hollow circular section is this. Pi by 32 into d power 4 minus d power 4. That is your IP. Then you know the value of this. This R is written as capital R is nothing but capital D by 2. The D2 goes to the numerator. All the simplifications you can do it. So D is 120 as given. So D by 2 means it becomes 60. Okay. So now you substitute that everything here. So convert this into Newton millimeter. If you convert this into Newton millimeter, into 10 power 3 you have to take. So this into 10 power 3 is your T value here. Then tau s is 60. IP is pi by 34 into d power 4 minus d power 4. Divided by R is d by 2. So you'll be knowing capital D value. You know the value of tau s. You know the value of T. Find out this value of small d. So if you simplify this, you will get small d. So small d is the maximum internal diameter that has to be provided for that hollow circular shaft. So okay, So this is what I wanted to explain you today. In the next class, I will be taking some more problems. So just go through the derivation, all those things here. Some more problem number 3, 4, 5. So many problems I have done. So you can just we will continue this in the next class. It's a simple chapter compared to your bending and shear stress. Easily you can score 8 to 10 marks from this. So they may give derivation or problem or both. So the only circular and hollow circular sections we are going to cover in torsion. So note the difference between torsional moment and bending moment. So bending moment takes place when the load is acting perpendicular to the beam. Okay, when it is subjected to transverse load. Whereas torsion moment will act when the moment acts along the axis, twisting. So it twists, it gets twisted. So that bar will get twisted. So you might have seen when people they want to dry the cloths at home. You might have seen you are going to dry the cloth using hand. You are going to twist that. You are twisting that cloth in one direction. You are applying in one end of the cloth. You are applying clockwise moment. At the other end, you are applying anti-clockwise. So then it is called as twisting. So in one direction it should be clockwise. Another direction it is anti-clockwise. So that's what I told. Here this arrow, here it is clockwise, but here you have to take anti-clockwise. Please make that change. So that here also and here also. Here also in this. So here if it is anti-clockwise here, it should be clockwise here. So that is known as the torsional effect. So at the ends of the shaft, we will be having same equal and opposite moments. So that is called as torque. So this is what I wanted to explain you today. Study this. Compared to bending stress and shear stress, this is a easy one. Torsion is an easy one. Problems are also a little bit easy. To discuss some more problems in the next class. Now let me take the attendance. 1828.
Present, sir.
30.
Yes, sir.
19002. 002.
Yes, sir.
005.
Present, sir.
006.
Present, sir.
7.
Present, sir.
9. 009. 10.
Present, sir.
11.
Present, sir.
12.
Present, sir.
13.
Present, sir.
16. 17.
Present, sir.
19.
Present, sir.
21.
Yes, sir.
Okay. Instruments. We'll continue in the next class.